Writing and evaluating a function modeling continuous exponential growth or decay given doubling time or half-life. In this video, we're looking at the other direction. We know the doubling time or the half-life, and we are trying to go back and find the growth rate and use that to solve a problem. So in this particular case, I'm switching over to bacteria growth just to get a glimpse at the other direction of things. The number of colonies of one particular species of bacteria growing on a petri dish is observed to double every 37 hours. And I didn't write down the question, but the question here is asking, what is the growth rate of this bacteria? And then we'll use the growth rate to answer a couple of additional questions. But once again, whenever you are dealing with exponential growth or decay, that means you're looking at something that follows this model. A equals A naught times e to the RT. In this case, we are given the doubling time. The doubling time is the time it takes for A to become 2 times A naught. So I can substitute that in and call that 2 times A naught. And again, I don't know what R is. That's what we're looking for. What is the growth rate? But I know that the time double is 37 hours, so I can plug that in for T. And if I copy this equation onto a clean page, then we can continue from here. Much as we did trying to solve for the half-life, we can divide both sides of this equation by A naught. And we can use the natural log to get rid of the exponential. In this case, that gives us that the natural log of 2 is equal to 37 times r. My calculator is happy to tell me what the natural log of 2 is, and then I need to divide that thing by 37, and I get that the growth rate in this case is 0.0187. That's 1.87% growth rate, and hourly growth rate at that. Right. Knowing that, I can now say in general that A is equal to A naught times E to the 0.0187 T. Right. This is the formula that tells me the number of bacteria on the petri dish given a starting amount of bacteria and a time that the petri dish has been growing. Right. So a follow-up question. If a petri dish is seeded with 500 colonies, how many will be present after 72 hours? Here, we can use the equation we just came up with. And we can plug in our values. We're looking at a time of 72 hours, 3 days, so that's our T. We're seeding the petri dish with 500 colonies. That's our initial amount. So I have here A is equal to 500 times e to the 0.0187 times 72. And once again, my calculator is very happy to help me out here. Once again, instead of punching this number in, I'm going to use the previous answer feature because my calculator has a previous answer feature, and that makes life a little bit easier on me. Let's see, over here avoids the glare a little bit. So I need 500 times. On my calculator, e is hiding up here next to the natural log, so I'll hit second, and then my natural log to get my e key, and I have that decimal number, which is my previous answer. I'll just use that, multiplied times my time, which is 72. And when I calculate that, I get 1,926 and a half. But there's no such thing as half a colony, so I'll round to the nearest whole and call it 1,926 colonies.